Thank you, speaker, again. Next up is Lionel Parreaux. Is that right? I got your name right, Lionel Parreaux from Hong Kong. There's a lot of great type-based stuff being done from Hong Kong. I've always been a fan of it, and particularly at eCoop, and then here, a very strong group. And effectively what you're doing is taking the kind of type systems that Bruno and co are developing and using them for ownership, which I think, of course, is fantastic. We did write a paper, a column that nobody read. Nick Cameron wrote a paper about embedding ownership types in, he's scarpered, bugger. I don't need to finish my sentence, about embedding ownership types into higher order dependent type systems, but nobody read it, so that's okay. Neither a borrower nor a lender be. As the bard said, you have 20-something minutes without hesitation, repetition, or deviation.
All right, thank you. Yeah, let's talk about modular borrowing without ownership or linearity. And I'll start with a disclaimer. This talk is a bait and switch. I'm not going to talk about borrowing as you probably know it, right? So I'm going to talk about something a bit different. It's more like temporary freezing of regions, but morally it's something similar, right? And I'll mainly talk about now about a type system for achieving this thing and the properties of this type system that make it expressive enough to represent these kind of things, okay? So this hinges on representing static scope safety constructs and type inference for good type and effect systems, okay? And so the eventual goal is to also support something like Rust-style programming where you manage your memory explicitly and it remains type safe, but this is for another time, and today we're not going to talk about that. So scope safety, what do I mean by scope safety? Well, it just means that certain program entities should remain within their scopes, right? And there are many applications in programming where scope safety is important, such as stack-based memory management, exception handlers, metaprogramming, mutable state encapsulation, polymorphic type checking, etc., etc. And one of them is borrowing, right? You need to keep the borrowed references within the scope. They should not leak, otherwise you're going to get into problems. And so static scope safety is the discipline where you guarantee scope safety at compilation time. And there are many ways of achieving static scope safety. Some work better than others, but today we're going to talk about type system ways of ensuring static scope safety. And so, in particular, I'm going to show a system that has this very simple construct. I call it the tracked instance construct, where you initialize objects by using this funny binding syntax. So new is actually a binding syntax now. So here you're instantiating an instance of C and binding it to X, and then using X inside some expression E. And within E, the variable X actually has type X. So it's like an abstract type that cannot leak outside of this scope, of the scope of E. And X is, has an upper bound, which is C of whatever type arguments C takes, okay? So that you can still use it as a C, okay? We use a type inference approach to make sure that whenever occurrences of X leak, for example, it's passed to a function coming from the outside, or maybe it's returned, actually it's subcasted automatically to this C of arg type that is its upper bound. Okay, so references to C really cannot leak outside of this binding. Right, and then you can define the classical new syntax as a shorthand for immediately returning X, which immediately leaks it, and so upcasts it to a C type, right? And moreover, we want to track effects, okay? No surprises. So our typing judgments have a type, but also an effect after the exclamation mark. And so we make sure that the entry point of the program has type bottom, which is the bottom of the subtyping lattice, right? In this system, because we want to make it as simple as possible and as lightweight as possible with normal types to express effects. Or actually, we may want to make the main entry point effect IO or something like that, some base effect, right? And so you can compose effects together by using union types. And so this pipe character that I'm using here is a union type. So if you have two expressions that yield different effects, putting them together yields a union type in the effect position. And these are the normal union types. They're commutative, associative, idempotent. So if you union something with itself, it's the same as the thing, et cetera, et cetera. And we can use a shorthand that says the SROT is the same as S with no effects going to T, right? Because function types now carry effect annotations. And so we can use this system to track mutation. And the basic idea is that, say you define a class that has a mutable field, so that's a ref class, in order to store some mutable value inside. And you allocate it with the new construct. Then within this, the scope of this construct, you can set the value. Set r.value equals 42 is just a way of assigning the field. And the effect of this expression will be r. R is the variable type that was bound by the new construct, right? We make it as simple as possible. We just refer to the variable name directly as the effect. And then when you access the value, you also have the R effect. In this version of the system, we don't distinguish read and write effects, again, for simplicity. But outside of this whole binding, so the overall type no longer refers to R, right? Because R is fully encapsulated within this little program. So the overall type is unit, and the overall effect is IO, because that's the effect of the println. And so the below program is ill-typed. Here we're instantiating a reference and leaking it immediately, and then we're trying to assign its value. So remember that I said the type X will be upcasted to a reference type, in this case, ref of int, if it leaks. And so the effect itself becomes ref of int, right? But main wants bottom as the effect, so this is ill-typed. That's how we make sure that things don't leak, because things can actually leak, but then you cannot use them to write your applications, right? Because you cannot actually compile the main function. Okay, so this was actually another lie. What actually happens in the real compiler is that you don't get this as an effect type. Like, nobody wants to see these kind of things as an effect type. What we get is an extruded variable. It looks like this. It bears the name of the original variable and some extra metadata, so that the compiler can actually pinpoint where the extrusion happened, and it can tell the user, oh, actually, you know, this thing leaks, and it shouldn't end up there, right? So the ergonomics matter, right? We care about making good error messages and making things tractable for users. But theoretically, it is the same thing, right? In terms of theory, these two things are exactly equivalent. Okay, so let's look at an example, and let's look at how this gives us referential transparency of pure functions. So pure functions yield the same results when given the same arguments. And what I mean by pure function is a function whose effect is bottom, okay? And local mutation can be used to implement pure functions, right? So the state is completely encapsulated, and that's perfectly fine. It doesn't violate referential transparency. Say you have a map function coming from the list module. So list.map, it has this type. So it takes a list of A to a list of B by applying a function from A to B with effect E, right? And we want to define a new version of this map operation that passes to the function argument the index of the element that is being processed. This can be useful for various applications, and this is a function that you actually find in the HKML standard library. And you can do that by creating an index reference using the new construct that makes its mutability encapsulated within this implementation body, right? And then you can use that index inside the function that you pass to map, and you increment it as you go, so that you can pass the current index to the function f, okay? Is that clear? So this is just application syntax. List.map of something is just applying these things. Yeah, then, okay. So we can actually get rid of these effects, right? They're kind of annoying. You can say there's an ambient effect. This is not a new idea. So it makes the signatures much nicer to look at. So in particular, list.map and map.i have these actual signatures that don't mention any effects because there's nothing surprising that happens in terms of their effects. But effects have to show up where they actually matter. For example, if you have a stream, which is a lazily computed sequence, then you have to keep track of the effect because the effect is kind of delayed, right? So it's not as obvious as for lists. So we can use the same little system to encode exception safety. So for example, you can define a throw and handle combinators where handle takes a continuation which takes this exception of p type, which represent the capability of throwing an exception with payload p, okay? And then the continuation returns some result, and it's allowed to use e, okay? So, the effect e. And also, it's allowed to do other things than e, which is represented by this capital E. And in particular, this small e cannot leak into the capital E because E is less polymorphic, right? The continuation itself has to be polymorphic, and that's why it cannot leak its effect. Okay, and so then handle also takes a catch clause to catch whatever is thrown during this body execution. And the overall result, again, hides this inner effect. It encapsulates it, and it only refers to E because the effect has been handled. So this can all be expressed using simple combinators and using the simple type system that I showed, right? So this is how you would use it, right? Again, the notation of f of a, b, c is the same as f applied to a, b, c. And you can use throw inside this. And you don't need type annotations, by the way, when you use this combinator. So exception safety is guaranteed, right? So if you try to misuse exceptions, for example, by trying to throw exceptions within a stream that leaks outside the handler, of course, you get a problem. You get an extruded reference to the effect, and that fails to compile. Actually, what you get out of this leaky stream does type check, and you just cannot use it. If you try to actually compute the elements of the stream, then you get the bad effect that leaks out of the effect of your main program. So checked exceptions were a bad idea, I hear you say. And I answer, you were a bad idea. Okay, moving on. So here's how to design mutable collections using my little type system. You can define iterators, which work with some base effects and some mutable buffers. So buffers can push elements, can clear the buffer. You can iterate on them. Is that a good API? What do you think? Sorry? If fail, what? Oh, if fail.
This is the design of collections in version
Right, okay. Well, but this one is not a good API, right? I don't like it.
It is the first design of
Well, that's good to know, but it's also similar in Java. And in Java, what you get if you try to do these kind of things that I'm showing in the slide is a concurrency exception in non-concurrent code, which is magic, right? So you're trying to iterate on some array, you clear the array in the middle of iteration. Java is nice enough to catch this early for you. That's actually good. It's better than C++. C++ would just corrupt things randomly. So that's nice, but we still want to avoid these kind of things at compilation time, right? Not at runtime. And so this is how you can do it. What we want to do is we want to restrict the lifetime of the iterator by using the same trick of passing a continuation where the iterator can live and can be used so that we can use its effect within that continuation. But we want to prevent this continuation from clearing the buffer, right? We want to prevent it from using the effect of the buffer. So the effect of the buffer, because these are implemented as methods, is represented using this, okay? And so what we can say is that the effect of the continuation, the iterator taking continuation, can be either the iterator itself or some E, which is not this. So it's a subtype of not this. This is a negation type. And this guarantees that you cannot use the mutable buffer while iteration is ongoing. Okay? You can also equivalently represent this using an intersection type, actually. This is formally equivalent. And maybe it's more natural to some people. And so here's an example correct usage of mutable buffers. You can instantiate a buffer, then you push some elements in it, and then iterate over it. So this is the while loop, and you call next, and you check whether it's some, in which case you do some printing. Okay, that's perfectly fine. And then if you're trying to clear the buffer in the middle of it, then you get a type error, and this is an incorrect use of the buffer. So that's it. We achieved what we wanted to do. We can also split any parts of this code, which doesn't have any type annotation, into helper functions, because this system, which looks a lot like borrowing, is not like borrowing. Borrowing is syntax-based. It looks at the actual code of your current function, and that means that in Rust, you cannot extract arbitrary parts of your functions into helper functions, because it may stop borrow checking. Well, this doesn't happen for us, because everything is type-based, so everything is modular out of the box. You can nest buffers arbitrarily. You can have many buffers, and you can iterate on them in parallel. You can clear those that are not being iterated at the same time. It works, right? I tried it. This is implemented. It works because basically the trick we play here is that all of these buffer instance variables, they are disjoint, so that their intersection is bottom. Okay? So that's what allows you to clear a different buffer while iterating on the first buffer, right? Because the effect of clearing the second buffer is a subtype of not the effect of the first buffer. That's the same as disjointness. So what if you want to clear a buffer only in some situations, but not in others, as determined by some branching construct that happens within the iteration, which is something that you may want to do. And that's what Rust calls non-lexical lifetimes. It requires the borrow checker to become even more complicated to support it. Because we'd like to write this kind of programs, but this doesn't type check, because the clear happens while iteration is still ongoing. Well, you can just delay the clear, right? You can return a lambda, you can return a thunk, right, that does the clearing, but doesn't do it immediately, okay? So that the result of this overall expression is a function from no arguments to unit that does clear the buffer. And then you apply this function outside of the iteration. You see? Because it's all type-based, and everything is represented in the type system. And you can have a syntax trigger for it so that it becomes nice looking again. Say we have end it, which sounds dramatic, like you end it, and then you clear the buffer. And this is just syntax trigger for returning a thunk that will be evaluated after what we're ending, right? Good. Disjointness for safe concurrency can also be expressed thanks to disjointness in the type system. You just need to make sure that out of the two effects of the computations you want to run in parallel, one extends the negation of the other. You can pick its equivalent, right? E1 can extend not E2, or E2 can extend not E1. And then that the overall results of the function has effect E1 or E2. And this is actually very similar to, so a paper that's being presented at UPSLA this year. So how does it all work? There's no time to explain. Trust me, right? But I'll give you the high-level idea, okay? Very quickly. So we rely on Boolean algebraic subtyping, union intersections and negations as part of the type system with principal type inference. This is something we published in UPSLA 2022. And we slightly generalize it in various ways. We need higher rank polymorphism to achieve these kind of things I'm showing. And that's because these pseudo-dependent looking types are actually just higher rank types, right? It's just a way of saying for it, iter of t2, blah, 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 referring to it. And also we need to track effects, but that's actually easy. And there's this disjointness trick, which is that we implicitly pass everywhere a type that represents the union of everything that's bound in the current scope. So that whenever we create a new instance using the new construct, we can make sure that it's a subtype of the negation of that union, which is the same as saying that all of these tags are disjoint. Okay, they're equivalent to bottom. And this is not meant to be academic vaporware. We're actually working on building this in a real programming language. And the little syntax that I used for pattern matching within conditional statements, this is called the ultimate conditional syntax, and Loyo will present it at UPSLA later in the conference. Okay? We also use similar tricks for a paper that we present at GPC. And so the design philosophy of our language is just have cool features. That's the core design philosophy. So in conclusion, I showed how to do modular borrowing without ownership or linear types, meaning that it's type-based. You can refactor things fearlessly, right, to reuse the expression that you use in the Rust community. And borrowing is achieved through temporary freezing by making some continuations, bounding the effects of some continuations to be the negation of some other effects. And we don't actually track captures. We don't track capabilities in the usual way, right? Captures are completely unrestricted, and aliasing is unrestricted in this system, okay? We track effects. So as Colin mentioned, that there's this dichotomy of things, right? And you can do everything with simple effects, and that's actually a bit more expressive, I think. Okay, so that's it. Am I early? I went too fast.
Perfectly timed.
Okay, thanks.
New construct, which you introduced fairly early on, how does that relate to the kind of let region that goes right back to, you know, Phil Wadler's 91 paper on Wadlerism, or linear types of Wadlerism?
Yeah, we actually started from that construct, and we started basing everything on regions, but then we realized that this was not really necessary, and just using subtyping is enough, right? So it's a bit, that's why I say it's more lightweight in a way, because you
don't have on the slide where you say we're not tracking captures, we're not relying on substructural properties, but you're relying on subtyping, effectively.
Yeah, and we are basically playing the state monad trick, right? Which uses a continuation that must be polymorphic to ensure that things don't leak. You can view it as being more or less the same as this, except that we're in a context where we have a lot more flexibility in the type system thanks to subtyping, right? So thanks to unions and negations.
Yeah. Other people with questions? Student volunteer.
Hi.
Hi.
Thanks for the great talk, and this also looks like super nice work. I'm looking forward to reading about it. I wanted to ask a couple of things. So a few times during the talk, especially early on, you mentioned situations where you can type something, but the moment you use it, it will essentially be rejected. Right? So you have situations.
Yeah. So if you try to use new directly, so this one, right?
Right.
Yeah. It's definitely one difference. You can leak things, and if these things don't have effects, that's fine.
Right, well,
in this case, there's an effect.
Where you had the extrusion is like saying this is a type for something that you can't really get at, whereas the standard way of doing it would stop at the first.
Right. Yeah. We're a bit more flexible.
Okay,
to
but hang on a second. I had a different question. So, have you thought about whether it might be good to reject these programs up front?
Yeah, I've thought about it. And so in some situations, it might be fine if the features you're trying to encode permitted. But we have a lot of features like metaprogramming where you really don't want to do that because it's normal for things to leak out, basically, right? Sometimes you have an intersection of several things, and the normal thing to do is that when this thing leaks out of the scope of one of these intersected things, you get the other intersected things because the thing that leaks becomes equivalent to top, basically, meaning it's removed from the intersection, but you still care about the other things. So the leaking, the extrusion is the behavior you're expecting in this case. So it's a lot more flexible to do that. It allows you to do more things, such as metaprogramming, but also the other reason, which is also a very practical reason, is that we're trying to do principal type inference. And if you reject things, we want the type inference to be complete. So if you reject things when they leak, you're not actually typing all the programs that could be typed. If in the source program there was an upcast into some other type that's less precise, right? And also, in this particular instance of our type system, the new construct can be used for anything, including things that are not really tracked, that you don't care about their lifetime, right? And you want to be able to leak this, right? Remember that if you leak, say this could be some other type, right? And if you do new of that other type, and that's a pure type, you don't want to cause a problem here. You want to actually be upcasted to its less precise type, right? Does that make sense?
I think so, yeah. Thank you.
Yeah, Colin?
So I have a question. I think it's the next slide. That I know this is not the focal point of your talk, but I'm curious about this claim about these extruded scolums being exactly equivalent to the simple version. And I believe that they accept and reject the same programs. But one of the things I bumped into trying to do good error reporting for other kinds of effect systems was they're equivalent with what you accept, but like the structure of what extra stuff you plumb through actually becomes quite interesting. So what other stuff gets plumbed through in this alternative error reporting?
Right, so you're talking about ergonomics, right?
Yes.
From the user's point of view. Ergonomics are super important, and that's one of the things we haven't fully figured out yet. We want to generate error messages that precisely describe what goes wrong, and for this we need to keep track of lots of metadata, but it's something I cannot really tell you a lot about because we haven't yet properly implemented this. Yeah, so, but I know that it's very important, right? If you don't do the extra work of keeping track of things, then the errors are just horrible, right? It's just like, you don't know why things don't work, right? You have some effect that's top or something, and you don't know why. So, not a good ergonomic. Cool.
Anyone else? Questions?
Okay, so I thought this trick for avoiding needing the kind of non-lexical lifetimes was very clever. I like it a lot. But what happens when you can't push this straight into the continuation? So I don't think in Rust the only situation where you want non-lexical lifetimes is where this is the last thing that happens in the function.
Well, I'd like to hear about this. I don't know. Do you have examples? Well, we can take this offline, of course.
Oh yeah, we could chat at lunch or something.
I'd like to know if you have examples in mind about this, definitely. And to check if we can encode them or not.
I mean, at least an esoteric example off the top of my head, I think the borrows can end in different branches, even if you're inside a loop that itself is going to carry on iterating. I think this is allowed. So
okay.
Like the borrow can temporarily end in the middle of a loop, and then you can start the borrow up again. At least in the, I mean, we're going to hear about this afternoon, right? In the newer borrow checker in Polonius.
Yeah. So
you can do some pretty fancy stuff. Anyway, I'd be super happy to chat later.
Yes, let's do that.